So yeah, anyway, point being is that I found that like a lot of people have a bunch of hangups about math, right? And these are pretty deep emotional hangups for good reason. Because as far as I've been able to see, we teach math to effectively deliver on artillery fire, right? And so kind of math was taught essentially in one way for a long time. It was the old school, like Platonic, Aristotelian way, which involved the quadrivium, right? Which were and the trivium, which were like the 7 liberal arts that you could learn, right? So we had the 4 subjects, which is what quadrivium means, quad, which were arithmetic, geometry, music, and astronomy. And then we had the trivium, which were the kind of icing on the cake. So those 4 subjects were seen as the minimum bare knowledge you needed to do to know to affect change in the universe, essentially, right? And then to actually do that change in the universe, right? You'd have the trivium, which were the 3 things, which are grammar, logic, and rhetoric. And with those 7 things, you'd be able to be a properly educated person up until about the 1800s. And at that time, there's a huge shift in education where we decided that people need to be educated well enough, everybody, to operate on factory floors and to participate in industrialized militaries. And so at that time, we totally shifted everybody's mathematical knowledge from sort of a more geometric based approach, which developed people's like logical reasoning and, sort of abstract reasoning, to more of an algebra based approach where you'd be able to do on the spot calculations so that, again, you could operate artillery and other kind of sophisticated weapons of war. And that's kind of where we've gone since then, is sort of the reason why you learn math is to become an engineer or a physicist or something like that. And so geometry gets a brief mention, just long enough for you to get what you need for calculus, right? And then we roll right along. And if you don't get that far, then it's okay. We have calculators and stuff. You don't really necessarily need to know anything else, right? So that kind of, we have a huge disconnect with the past in that way. So what is sacred geometry, right? So something that is sacred is something that's set apart. It's related to holy, right? Which is also meaning to be set apart, right? So it's geometry that is set apart. Well, what's geometry? Geo means earth, and metry means to measure, right? So telemetry is measurement from a distance, right? If you've heard that word, it's kind of, what that means. Symmetry is the agreement in dimensions or due proportion, right? So it's sort of like measurement of objects with themselves, so to speak, right? So we have these 3 kind of ideas, and you could either think of geometry, sacred geometry, as the measurement tools, so the geometry being sacred, set apart, or you could think about it as measuring a set apart world, if that makes sense, right? So you have sacred geo, a sacred earth, or so a set apart earth or universe that we're measuring, like at the astral plane, so to speak, or a spiritual dimension, or a psychological dimension that's not physical reality. Or you could have the sacred tools to kind of go in this space. I think those more or less mean the same thing, and that's just me kind of riffing in a pun-like way off of those several terms, right? So in a certain way, in my opinion, geometry and algebra are actually not that different. People want to make sharp distinctions between them, geometry and arithmetic, but anything that you can do in arithmetic, you can do in geometry, and vice versa. In some ways, it's just thought about in different ways, essentially, right? So the kind of example that I want people to keep in their head, that I think will keep everybody more or less on this call on the same page, because we have all different backgrounds here on a spectrum of science people to sacred science people, so to speak, is astronomy, right? And everybody was pretty well through geometry able to communicate with each other in the ancient world using astronomical ideas and therefore geometric ideas. In fact, most of the things that we think of, like the Pythagorean theorem, which is a squared plus b squared equals c squared, that originally was thought of purely geometrically from top to bottom. We think about this as an algebraic derivation, but actually, like, you know, if you've heard of in an algebra class completing the square, this might have seemed like a weird abstract thing, but the way that people thought about this forever was in purely geometric terms, and you literally had a mini square that was missing, and so you were completing the square, right? So a lot of these things made a lot more sense back in the day before we kind of, you know, rolled into the current era where we're trying to get people just smart enough to be able to operate complicated systems, but not so smart that they like question the system and stuff, right? So there we go. So math is the study of patterns. And a pattern is sort of a rule or you know, a way that we describe different qualities that seem similar amongst different objects, right? So for instance, like it's just a categorization scheme, right? So it's a way of defining a category in a precise way. So even numbers are a great example of a pattern, right? Because they're all divisible by 2. And we might think of this as you start with 2 and you add 2 more to it, and then you add 2 more to it. And that's one way of describing that pattern. The other way is to say, hey, take any number and divide it by 2. That's another pattern, right? A square is a pattern, right? So you can have different types of pattern, whether it's like whether it's sort of the shape of an object, or it's the quantity of an object, or a quantity of a collection of objects, right? Another pattern is a symmetrical pattern, like so all humans and a lot of animals have twofold symmetry or mirror symmetry down their bodies. So that's basically what it is. And now if you take all these patterns and you collect them all together, you can start to find patterns among these patterns. And that's really what mathematicians do all day, every day, right? Is they sit there and they come up with patterns. And the thing about patterns is that none of them actually exist. It's kind of interesting that in this morning's talk, we talked about you know, this quote that Andrew brought up. What was the quote about again? I forget about it. It's something about like beauty or whatever, right? And I was thinking, or no, it was about in music or in art, you know, a lot of times if it's too perfect, it's not really that great. You want a little bit of imperfection in your music, otherwise it just doesn't sound right. Well, I think that's one of the ways to think about that is that patterns are not real, and we don't really like things that are too synthetic, right? So a pattern is this abstract idea that doesn't actually exist in the universe, right? But it's oftentimes informed by what exists in the universe, right? And so there's some patterns that are more closely linked to reality, and others that are just so far out there. It's like, oh, okay, like, you know, that's not even applicable to the real life. And a mathematician would say, yeah, absolutely, I don't care if it's applicable to real life. I'm just studying how these things interact with each other, right? So I wanted to kind of start with a totally non-geometric situation, right? Which was the following thing. And it was to kind of challenge this notion that we have that everybody says that we use base 10 because we have 10 fingers, right? And I say, well, that's not really, it's a pretty unsophisticated way of counting, right? Because you're just pairing one thing per one finger, right? I can count to 10 on one hand, right? And you can do it really without any ambiguity, right? And so what you do is you start with your hand like this. From your perspective, and you know, if you follow along with me, you can go 1, 2, 3, 4, 5, and then you turn your hand over 6, 7, 8, 9, 10. So there you go. You can count to 10 on one hand. You can count to 20 on two hands unambiguously that way too, right? So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then on your other hand, you don't even need this hand anymore. You got 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? So a lot of folks will say, well, hold on. The reason why we did the 10 finger hands is you can communicate far away. Well, I don't know how this is ambiguous far away, because if putting fingers up and down is ambiguous, then you can certainly see the orientation of the hand from just about as far away, right? So there's all these ways in which, you know, we have notions like are really ingrained into us that, you know, they are kind of fake, you know what I mean? And there's lots of math that sort of frees us from our initial intuition around these things, right? So my intention here actually isn't so much to talk about the sacred part of the geometry, but to talk about a little bit more of the geometric aspects that I think people find really scary, and hopefully navigate everybody through them so they're a little bit less scary. So let me see, where are we at? I'm trying to figure out if I want to, maybe I'll just tease this instead. So one of the kind of basic formulas that seem really obvious is 1 + 1 = 2, right? And it turns out that this is not very easy to prove, right? Like in a lot of ways, people say, "Oh, well, no, this is just obvious," right? I'm like, "Well, what do you mean by obvious, right? Like, why is this? What is underneath this that makes it so darn obvious, right?" Because for the most part, people think they really understand what you say 1/2 means, right? And I kind of challenged this person. I was like, because they were talking about imaginary numbers, right? And they were trying to say that imaginary numbers, which is a number that's generated by taking the square root of -1, so the square root of a negative number, is a fake number, right? That it's imaginary. I'm like, well, 1/2 is kind of fake too, right? And they were like, what do you mean? And I was like, okay, show me half of something, right? And I had a piece of chalk. I said, show me half of this piece of chalk, right? And they said, okay, fine. They broke it in half. I'm like, well, now you have 2 pieces of chalk. Where's the half, right? So there we are, right? And then I was like, but 2 is kind of fake too, right? Because show me 2 of a thing, right? And they were like, well, I have this piece of chalk and that piece of chalk. I'm like, yeah, you have 1 piece of chalk and then 1 piece of chalk. You don't have 2 pieces of chalk because they're different, right? So 2 is something that you superimpose upon multiple objects, right? It's something that you've decided, I'm going to call these 2 objects the same. And so now I have 2 of them because each object is unique, realistically speaking, right? If you could distinguish, if you can't distinguish something from each other, it's the same thing. And so you only have 1 of it, right? So actually the notion of 2 is superimposed upon the universe by us because we decide that there are 2 different chairs and that a chair is a thing, right? So what this is actually saying, right, in 1 + 1 = 2 is that I have 1 object, and then I've deciding that another object is similar enough to it that now I've got a quantity of 2 of this category of things, right? So to clarify it, we have 4 symbols here. We have 1, we have 2, we have plus, and we have equals. And I'll probably gloss over some of this. I just wanted to kind of raise this question in people's heads because this could be basically a talk in itself. But essentially, 1 is relatively easy to deal with. 2 is a little bit harder to deal with. Plus is relatively easy, and then equals is easily the most difficult and tricky symbol up on the board right now. And again, that sounds counterintuitive, but when you really dive into what does it mean for 2 things to be the same, like that's actually quite a hard problem, it turns out. So that's my claim, is that every number except for 1 is fake, and kind of made up and superimposed upon us by us. Let's see here. I'll skip ahead to this notion of the shepherd's thing about counting, and then I'll move on to the actual geometric side of things. So way back forever ago, if you look at very old societies, right, they don't necessarily have numbers past 3. Right. And it was really interesting. I saw there was this Australian anthropologist who was talking to some of the Aboriginal folks, and he was like, how many children do you have? And he was like, oh, I have many children. He's like, really? Could you, what do you mean by many? How many do you have? And so he was like, okay, I have Aaron, I have Noel, I have Sarah, I have Mary, right? And so what he'd do is he'd make little hash marks in the ground to as he said, the names of his children. And that actually, it turns out, is the way that mathematicians count things for realsies, though, right? We think about numbers as being the way we count things, like 1, 2, 3, 4, but those are just the name of the successive object, right? Or that is to say that the thing after one is two, right? So once you've established that you have one thing, then you say two, and then you say three, and we've kind of agreed on that's what these things mean. You could do the same thing with A, B, C, D, E, F, and actually ancient people did it that way, right? If you know Greek or Hebrew or many of the other Egyptian, a lot of alphabetic systems or systems without vowels, right? But they're abjads. A lot of those systems had canonical values for each letter, like alpha, beta, gamma, so on and so forth, right? But you can actually count without any of these number words in the same way that that Aboriginal dude, named off his children. And essentially what you do is you imagine a shepherd, he's got a bag of stones. You just put a bunch of stones in there. You empty the stones out on the ground, and as your sheep leave the pasture, you just put a stone each time a sheep goes through the gate. And then you zip up that bag, put it on your side, and when it's time to bring the sheep back in, you bring the sheep in one at a time, and then you toss a stone out. And if you have stones left in the bag, then you're missing some sheep. So you don't actually have to have any numbers to count things, right? And it turns out that this counting system, although it's really simple, also allows us to distinguish that there's multiple different types of infinity. So it turns out that the counting numbers, like 1, 2, 3, 4, 5, 6, have the same number of numbers as the fractional numbers, like 1/2, 1/4, all those guys. And that there are fewer counting numbers than there are real numbers, right? So that like pi, square root of 2, all of those numbers with irrational, that with an infinite number of digits on one side that never repeat. It turns out that there's way more of those numbers than there are counting numbers. So infinities have different sizes, which is a hugely counterintuitive result, and caused a huge amount of philosophical and theological consternation when Gregor Cantor came up with this idea. Like literally, he was getting death threats. There's a bunch of religious people that are not stoked on that. Because obviously, if there's a number of different infinities, you have to ask yourself, well, which infinity is God, right? Like, how big is God, right? And then that opens up all sorts of cans of worms that nobody wants to deal with. So there you go. All right, so this is the part that I wanted to actually get to, just like a little teaser trailer for a potential different talk. So what we have right here is essentially everything you need to do very basic trigonometry, right? And trig is pretty scary to a lot of people. I don't know, it's got a scary name maybe, like, essentially though, this right here gives you the geometric proof for converting, the sine and cosine back and forth from each other in terms of it gives you basically the angle sum, not the angle sum formula, but the 90-degree rotation formula, right? And what this diagram also kind of allows you to calculate is that essentially if two waves are, how do you say it? It shows you if two waves are at right angles to each other, so to speak, right? If they're shifted 90 degrees from each other, then they become the same thing, right? So that the cosine cosine of one angle is literally sine of another angle, just minus 90 degrees. Now, I will explain that here in a bit. It's just kind of setting it all up for this particular diagram and everything. Let's see, where is cursor? It is over here. And again, I've been sort of pointing out this point a couple of times, but essentially, like, a lot of our notation and a lot of our words that we use to describe mathematical concepts are really just very stupid, certainly with our current education system. It used to be that, like, back in the early 1900s, you'd have people who learned Greek and Latin, right? And you had a different set of physical activities, right? Like, so you would go learn how to maybe shoot a bow and arrow, right? If you're back way back, in Babylon days, what are you going to do? You're going to ride horses, shoot bows, plow fields. There's all these different things that, for us, modern times are not really baked into our body intuition, right? So, for instance, if I talk about driving a car, you actually get bodily responses, and I kind of have these examples here, right, where if I asked you to show me the motion of answering a phone, right? What would you do? Show me answering a phone. Yep, boom. Everybody's same motion, but it's locked in, like you can feel it instantly. You don't even have to think about, I got to raise my hand. No, your body just does it, right? You don't even think about it. That's how deeply ingrained a lot of these older school things were for people, right? Is like, if I ask you to, show me the motion of firing a bow, how would that look? Yeah, exactly. All of you are doing it wrong. So the way that you fire a bow, and I'm not like an expert or anything like that, but the minimum is you have to bring the string up to your eye, right? And you fire from here, right? And you get the 3 fingers and all that stuff. And boom. Well, that's something that like every hunter-gatherer since the beginning of all time would have at some point probably done, right? So that's something that is common knowledge to the ancient people and not common knowledge to us, right? Like the stars in the heavens are not common knowledge to us, right? But to everybody else, the lights go out at like 4:30 at this time. You would have seen the entirety of the stars because there's no light pollution, right? So everybody would have at least kind of known some of the stars. They might not know the deep meaning behind the stars, or couldn't have picked out every constellation maybe, but they probably could have picked out most of the constellations, right? They would have had intuitions around firing a bow and around hunting and all these things, and we just have lost that. And so that's the huge issue, right? Is that a lot of what was intuitive for the ancients, and they sensibly named these things, are less intuitive for us now. So let's go to the next slide. Oh no, skipping ahead way too far. So let's talk about drawing a bow. See this guy? He's doing it right. Boom, right to the cheek. So let's break down a bow and arrow. Zoom in. We'll ignore like the particulars of the picture, and I will make an ideal bow and arrow here. And then we will color some of the stuff. So this line right here is the bow at rest. This line, do I have a mouse? Okay, there we go. So this line right here is the bow at rest. This is the bow intention. This is the bow intention again, because of the, it doesn't really curve quite as much until you put it in tension. And here's the arrow. So we have a bow and an arrow. Then if I pull out the dude just to see the diagram better, we can very clearly see we have an up and down thing. We have this bow, which is a perfect circle in this case, right? It's a chord of a circle. This obviously is not a perfect circle, but we're pretending, right? And so in old school geometry, you only had 2 tools, right? The Greek geometry, as we think about it, you have a compass and a straight edge, right? The compass makes circles, the straight edge makes lines, and these 2 things fit together and give you pretty much everything you can get at geometry, right? So essentially what it comes down to is that old school geometry is asking what sort of shapes can we get, and what sort of ideas can we pin down using just lines and circles and putting them together, right? So for our purposes, the compass is like the bow, and the straight arrow is the straight edge, right? The thing that lets us draw lines. So it turns out that if we break all of these things down, right, we have one object that is a dual object. It's in a duality, right, with itself. It's composed of a bow along with an arrow. The arrow has 3 parts to it. It's got the shaft, the tip, or the point, or the base of or the nock, right? And mathematically, this is kind of telling us that every arrow has what we would call a foot, if we're thinking about it in terms of vectors, right? So it's got a starting point, it's got a direction that it's aiming at, and it's got an end point that kind of tells us where to stop. Then the bow has 2 to 3 parts, depending on how you've constructed your bow. It's got the limbs, which is the spring that actually puts the arrow forward, and it's got the string, literally a cord, right? Now, the geometric terms for sine and cosine come from the Latin sinus and cosinus, right? Now, this is actually a mistranslation of Sanskrit, essentially, right? So they actually messed it up back in the days. There was sort of a medieval guy that read the Arabic and thought, oh, it means this word and not that word. They messed up either the Arabic or the Latin, right? It used to be that the word that we call sign meant literally bowstring in Arabic and in Sanskrit, right? And they would talk about the other thing, the arrow, as the co-bowstring, right? And anytime you get a sort of object and a co-object, you're talking about a duality, right? Two objects that imply each other necessarily, right? Like an arrow doesn't really, a bow and arrow, arrow type doesn't really make sense without the bow, and the bow doesn't really make sense without the arrow, right? They actually require each other to complete the entire object. And so whenever we get whenever you see the word like codependent, right? Literally the bow and arrow are codependent, right? They require each other. And so similarly, when you see sine and cosine in geometry, that's what you end up with. And I'll kind of demonstrate that here with the picture. So we have an angle. Our angle is theta, which is just the letter T. So theta. We're going to focus right here on this center point. And there we have our sine and cosine, right? So we decide to just say that for simplicity, you could define the sine or the bowstring as the full bowstring, but it turns out that it's easier if we just think about the half bowstring and call that the bowstring that we're focused on. And then the cosine, right? The element of the sine that kind of completes the bow is this portion right here, the back half of the arrow. The reason why we focus on the back half of the arrow is because what we're really trying to do here is we're trying to say stuff about the circle, right? And so this circle doesn't change, but the length of the arrow could change. But this length between the bow where the arrow intersects the line of the circle, right, and the midpoint of the circle, the center of the circle, right, this part is always the same, more or less, right? So we'll focus on that guy. And again, to kind of tie it back to our notion here, this bowstring really is lined up with the compass, right? That's the thing that draws the circles, and then our arrow really is the straight edge. So a little bit of very light math here. Let's talk about the 90 degrees here, right? So if we look at this rectangle, right? A rectangle is a shape where all the corners add up to 90 degrees, right? Now those corners, if we drew a line from end to end, we've split up the 90 degrees into two sections, right? Which I'm calling theta and phi, which is F and T, right? So theta and phi, and we're just saying that, you know, since we've split up theta and phi into not really half and half, but into two parts, that when we add them together, we get 90 degrees, right? Or to say it a different way, that phi is equal to theta minus 90, right? That is to say that if we took 90 degrees and we removed theta, then we would get the remainder, right? So now notice from the way that I've labeled this, right, that with our sine and cosine, right, we had theta defined as sine and cosine. Well, this is a rectangle, right? So we know that the sides of the rectangle are the same, right? So if we look at it at the left side and the right side, that means cosine of phi, right, which was kind of like if you imagine a bow pointing down, like our previous one, then we know that the sine has to be the bow and the cosine has to be the arrow, right? Or sorry, it's pointing up. So actually we're shooting up in this case. And so that's why we've labeled sine of phi on the left-hand side sine of phi as the top and cosine of phi as the left. So what we see here is that cosine of theta equals sine of phi, right? And cosine of phi equals sine of theta, which is literally just taking our bowstring and pointing it horizontal versus pointing it up, right? Like nothing has changed except for the labeling of these various signs. But, you know, essentially this is presented as some sort of profound fact in geometry class, you know, partly because of all this notational nonsense, right? Like if we had taken all this notation and we tried to do this proof algebraically, which frequently is the way it's presented, it's way less intuitive than if you're just able to visualize all of these objects and realize that the sine and cosine are a relative measurement to where we're pointing our bowstring, right? And that's all we're really saying, is that when you rotate something like this, then the symbols sort of are like that. So are there any questions so far? I know that I've just been kind of going with no questions. I've been totally steamrolling over this entire thing.
The one thing was you said you pointed out the bow.
No.
The circle doesn't change, but actually that's what creates the force, right? The circle bending backward.
No, yeah, and sorry. So I was just pointing out that given my diagram, right, we're not worried about the circle changing because the rules lawyers amongst you would be like, well, when is it actually a circle, right? You know, because bows, especially the kind of bow I was showing there, is not necessarily ever going to be a circle or even approximating a circle, but precisely, right? So and some of these are kind of metaphors in that way, right? Like it's you know, it's obviously not a perfect well, and actually it's not even clear that they would have necessarily known that difference. It's not that the ancients were ignorant of such things, it's just not clear that like they would have had the scientific rigor to even distinguish that sort of circle from whatever shape that actually is, right? Like a physics person could tell you a lot better. And in fact, there's a lot of controversy in the King Solomon's Temple, right? There's a little verse where it says, it kind of gives a dimension of a well that he has. It was a circular well. And it basically sets up the dimensions of the well so that it sort of is very bad approximation for pi. Pi is the, you know, ratio between the diameter of a circle and its circumference, right? And this pi was known about for like literally ever. And there's a lot of debate about whether the Hebrews got it right or wrong, or how right or wrong they got it, you know, and frankly, it kind of doesn't matter for the story. They were just kind of giving the dimensions of what it was, and, you know, good enough's good enough at some point, right? You know, as with any like physical measurement, there's only so far that you can go with intolerance to really be able to get everything sorted out, right? So another thing I wanted to bring up that I have not brought up up until this point is kind of the question was 90 degrees, right? What is the deal with a circle having 360 degrees, right? Because it could have been 100 degrees. And in fact, Napoleon tried to make it he tried to make it 400 degrees. He called it grade, right? In the French Revolution, and this is pinnacle of crappy Enlightenment thinking, the French Revolution, they tried to make literally everything decimal, so base 10. So, you know, they got through on some things like the metric system, right? But they didn't get through quite on everything, and they failed to update, so to speak, the really ancient 360-degree circle into a 100 or 400-degree circle, right? And the reason why they did that is that it's actually a pretty dumb system, honestly. So what is cool about 360 degrees, right? Well, the Babylonians, and I was going to have some slides on this, and then I forgot. So the Babylonians, they were the guys that did the cuneiform, right, with the clay tablets and whatnot. They didn't have a fractional number system, so they didn't think in terms of like 1/2, 1/4, whatever. They actually had a decimal system like we do now. But since they had clay tablets, they wanted like a really easy system to do calculations on, because they couldn't just be doing like easy calculations like on a piece of paper like we could, right? So they had a decimal system, which meant that they needed to divide things all the freaking time to figure out how many decimal points out their division was. So division had to be pretty easy, because the issue is when you have something like base 10, right, you have a lot of repeating decimals, right? So essentially, how many different digits can you divide 10 into to not get repeating decimals? And it turns out it's pretty bad. But with base 60, which is what the Babylonians used, you got way fewer repeating decimals, right? And the beauty of 60 is it's divisible by 2, 3, 5, 6. It's highly divisible. So, I would propose that the correct base system to use, in my opinion, is base 12. And then you'd make metric based off of base 12 because, that way, and actually this is the way we used to do it, right? So the non-stupid parts of imperial measurement system, the imperial measurement system, use this system, right? So a dozen or a gross, right? So a dozen is 12, right? Well, this is why a lot of recipes would say use a third of or a fourth of or, whatever the heck, right? Is because they're trying to fit it into that base 12 system. So anyway, once you have 60 and you multiply 60 degrees times 6, you get 360, which is what they did. So they basically, that's why our circular system, that's why our degree system on circles uses 360 degrees, is because the Babylonians used, or the Sumerians and Babylonians used base 60. They were literally the first astronomers. And then once you have base 60, which is highly divisible, very easy to compactly put onto a clay tablet, essentially. You multiply that by 6, which is, if you have a 60-degree angle on a circle, then there you go. And then 6 times 30, or 6 times 60 is 360. So there you go. All right. Now let's talk very briefly about the Pythagorean theorem. So the Pythagorean theorem involves a right triangle that has 2 sides that are smaller and one side that's bigger. The bigger side is called the hypotenuse, and the other 2 sides are called the legs of the triangle. Oh, did I repeat the slide? I think I repeated the slide. So notice that I've drawn some squares around the triangle, right? And so that means that all the side lengths are the same because that's what a square means. And so we've got A's and B's and 1's popping all over the place. I've noted what the areas are, right? So we have A squared, B squared equals 1 squared, right? So essentially, I have the algebra down there, which is the A squared plus B squared equals 1. The claim is that, basically these two areas sum up to this area. And I'm not going to prove that because it's actually a little bit involved. But I want to return to that first figure that I showed you, which is this trigonometric figure, right? So if we took this this cosine, right? Remember, we have the bow and we have the chord, right, which is the sine. And we took this square here and we found the area of the square. We have sine squared, right? We take this side, which is the cosine. This is the bit of the arrow that we care about. And we square that and we get cosine. Using the Pythagorean theorem, we find that these 2 guys are equal to 1 squared, and 1 squared is just equal to 1. So that means that cosine squared plus sine squared equals 1, which is called the trigonometric identity, right? So let me see, is this, nope, that is a slide in action. So essentially what we found actually is if you're in geometry, if you're in trigonometry, these are basically the only 2 things. Everything else is just a bunch of notational stuff to be kind of a shitty IQ test to filter people out, right? And frankly, that's really what it ends up being, right? Because it could be way simpler, kind of as simple as this. Now, solving problems with it becomes difficult, but solving problems is always difficult, right? So it's not really, the notation really shouldn't get in your way, essentially. So if you had trig, like that's basically it. Like this tiny diagram here pretty much puts together the fundamentals of what you would need to do the vast majority of calculations. So let me see. I think I will go ahead. There's some other stuff I could talk about with symmetry, but I think I'll leave it there and open up for questions, or if anybody's confused, I'll be very happy to go back and recover stuff. But otherwise, if people pretty much understand what's going on, then we're in good shape. Yeah. So the numbers that we came up with first were counting numbers, literally the numbers that we would use to pair with objects to count them, like we did with the shepherds, right? And then the next wave of numbers to be invented were rational numbers, right? And they were numbers in ratio to each other, right? So they weren't necessarily like it's a cute pun that they're rational, right? And that we have reason being rational, and I'm sure that there's some etymology there that combines those potentially, but essentially what rational numbers are is they're numbers in ratio to each other, and that actually kind of makes sense because 3/4, right, is 3 against 4, so to speak. It's not quite that, but you know, there's a whole different way of representing rational numbers, basically fractions. You can think about it like fractions, but specifically they're ratios of integers, right? Or ratio of counting numbers, right? So everybody was really happy with ratios of numbers and counting numbers. And then all of a sudden, people started to come up with other numbers that nobody liked, or at least the Greek philosophers really disliked. And so negative numbers, or were given negative numbers because they were like, we need a mean name to call these numbers that I don't like very much. And so that's literally why they were called negative as opposed to positive numbers, right? It's just straight up slander. Okay. So we have our negative numbers that like, and the notion was basically the stupid reason given was like, these numbers are useless and dumb because we can't have negative of anything, right? But then the accountants are like, well, dude, I can tell you, you have negative money that you owe me, right? And that actually is a kind of smart observation because essentially what we're saying is that numbers could have a direction assigned to them. You could either say that you're projecting out from yourself or you're projecting in towards yourself, right? And if you owe me something, that's a negative number with respect to you, right? Because it's coming in towards me. It's a positive number with respect to me because I'm getting the thing, right? So fair enough. All right. Well, then there are these things called essentially like if you have a right triangle where the two legs of the triangle are 1, then the Pythagorean theorem gives us the length of the hypotenuse being 1/2. Or square root of 2, right? And it turns out that it's impossible to represent square root of 2 in terms of ratios of integers, right? It's not a rational number. And so they were mean again, they called it an irrational number. And the pun kind of follows that, you know, that's irrational as opposed to rational numbers. So another mean name that we give to irrational numbers. So finally came along people that are like, well, hold on now. What if I'm taking square roots of numbers? So if I take a square root of 4, right? I know what the solution to that is 2, right? Because 2 times 2 equals 4. It's the root of the square, literally, right? You know, the side length. But what if I took -4, right? So the question is, if I take the square root of -4, what 2 numbers multiply together to give 4, -4? Well, the only 2 numbers are -2 and 2, right? Because of negative times a negative is a positive, right? If I tried to take -2 and -2, I would get +4, right? So the sort of number that would cause me to get -4 is imaginary. It doesn't exist, right? Although it does exist, it's just a rotation by 90 degrees off of the real number line onto the imaginary number line. And the first mathematicians to you know, to develop imaginary numbers, we're trying to solve cubic equations, right? So equations in the form of x cubed plus x squared plus 1, right? With some constants out in front of everything, right? And he found that if you took these funky numbers that are square root of -1 or square root of -2 or whatever, you could actually, as long as you held together some rules, right? As long as you multiplied or divided them by certain rules, you could get real numbers at the end of it for his formula, right? And that was the first time. And of course, there's a huge controversy. Everybody's saying, "Oh, this is going to end God," and you know, freaking, this is the end of civilization. But you know, civilization persisted, and in fact, got better because it turns out imaginary numbers are hugely useful when talking about rotations, right? Of these of sines and cosines and whatnot. And so since they're really good at describing rotations, physicists have used them to describe oscillatory systems or waves, right? They come up in all sorts of physical equations all over the place. So we've recently had a talk on quantum physics, right? And all quantum equations are given in terms of imaginary numbers, because it turns out that the algebra required needs sort of these complex numbers. And sorry, a complex number is a real number plus an imaginary number. But anyway, that's maybe a different talk that I should give. So yes, Bill, that's kind of the answer of what's an imaginary number. Anybody else online? All right, people being shy. Yeah.
So, give us a broad statement of, I mean, your talk is sacred geometry, and you talked at the outset about how geometry was sort of glossed over. So could you give us a broad statement of, in your view, the significance of geometry, or just kind of what you're getting at here in a broad brushstroke?
Yeah, so the broad brushstroke here is to kind of so when I look at a lot of sacred geometry stuff, essentially the issue is that a lot of the symbology that they give you, right, is true, but the descriptions are kind of surface level, right? Because there's way more structure underneath all of the different reasons for the sacred geometric topics, right? Than kind of meets the eye, right? And really the what I wanted to really emphasize through this talk actually wasn't this last slide. This is kind of like a nice little icing on the cake. It's more the dualism, right? It's because there's a lot of dualism in sacred geometry. So for instance, the Platonic solids, right, are a dual set, right? That is to say that if you took the points of all the solids and you turned those points into faces of the solid, and you took all the faces of the solid, turned it into points, you get one of the other Platonic solids, right? So each Platonic solid can be kind of converted into one of the other back and forth, right? When we build like the flower of life, right? That involves like all this geometric stuff, but like unless you really are appreciating like the underlying geometry, like the mathematics behind it, it looks pretty and it kind of makes sense, but I've noticed that folks just necessarily miss a lot of the underlying geometry, basically that would be totally obvious if we actually taught geometry in school, right? And so so I will do an actual talk on actual sacred geometry, right? But given this sort of understanding, right, of where some of this geometric stuff comes from is really helpful, because here's the issue is that like actually when you get into the geometry side of things, right, it ends up being pretty tedious to step through a lot of the proofs, right, of why things are the way they are, right? Like you want to, so the idea here is to really see how well people can understand some of these things through purely just pictures, and then throwing up some symbols and then hinting that they're kind of the same thing. So basically the after this talk is running around to everybody one-on-one and seeing how much of this stuff just totally went over people's heads and how much is just kind of entertaining noise, right? And that's fair enough, because given this talk, now I can calibrate up or down, like whether I need to just go pure pretty pictures and just totally ignore the math stuff, or like if you can bring in the math as long as you have sufficiently pretty pictures, right? The other thing too was to just kind of emphasize the history that's been lost, and a lot of the reason why math is so difficult for people. It's like, because a lot of folks tell me, they're like, man, when you explain it, it makes sense, or like, I feel like I could be better at this, but I just had a bad teacher. I'm like, yeah, invariably that's the case. And it's not just that your particular teacher is bad, it's just our whole approach for math is wildly incomplete, because we have all these intuitive models that math came from, right? It wasn't just dropped on the sky for us, like we came up with this shit, right? And so when you actually drill back into the history of where all this stuff come from, like the Babylonians were looking at the sky and they were trying to solve a particular problem, and that's why they came up with 360 degrees in a circle. Or like actually the parts of a right triangle that are sine and cosine come from a bow and arrow, right? And you know, that leads us into the duality of what a bow and arrow is, and that actually gives us insight on duality itself, right? That, you know, we you know, and maybe part of why duality gets a little bit slippery is that a bow is an object and an arrow is an object, and the bow and arrow is sort of a composite object, right? But at the same time, like, you wouldn't call it an arrow, you'd call it a spear, right? And you wouldn't call it a bow, you'd call it a spring, right? So there's something really fundamental philosophically about, you know, these two things coming together and modifying the underlying objects when they become this one synthesized object, right? And so the other point of this talk is to kind of demonstrate that math can help cut through a lot of really hairy philosophical concepts that otherwise are really difficult to tangle through. I get really upset at philosophers that like spin in circles forever. I'm like, oh my God, if you just knew a little bit of real analysis, like the whole problem that you're trying to wrestle with would be no issue. So sure. So yeah, oh, sorry. So the question was for the deaf amongst us. The question was, if you can use sort of practical, real world, physical things to teach math through, can you use spiritual or religious or other symbols to teach math, right? And I think the answer is yes. So I've been doing this class on breathwork, right? Which is sort of essentially it's how to sing, but it's taking something physical like breathing, you know, like singing, and it's going into your brain and relabeling some of the parts of your body, right? Or pointing out in your head like where where your diaphragm is, right? What it does. And so it gives you a mental map of your body that you then can apply to your body and use your body differently, right? So you go from a physical space to a mental space and back to a physical space again, right? The issue with math is that it's already pretty abstract. So it's a mental space, right? And if I went to a spiritual space, it's hard to find rally points in spiritual space, right? This is kind of what theosophy is all about, right? And other sort of esotericism like the Golden Dawn or like Freemasonry or even Christianity or paganism or whatever. They're supposed to find rally points so people can find each other in spiritual space. But in an eclectic group like this, it really is difficult to find these spiritual waypoints to be able to effectively teach the math that would help you reorientate yourself and find points in spiritual space again, right? So what I tried to do with this talk is I tried to go from a mental thing to a physical thing and back to a mental thing. And I found that usually works because a lot of these mental principles we developed based off of physical reality around us, right? So another sort of upshot of this talk is to kind of demonstrate that math is fundamentally an orientation tool, right? Like geometry, right? Geometry is literally about measuring Earth or reality, right? And so it really is meant to find your way around the universe, right? And I found that math is a really good tool for finding your way around religion, philosophy space. And actually, we do this all the time, right? Like churches are symmetric for a reason, right? They're cross-shaped for a reason, you know? The I Ching has like trigrams and hexagrams for a reason, and they're arranged in those ways for a reason. It's like we use these mathematical tools as an explicit like compass, and and not just compass in terms of the navigational one, but compass also in terms of the drawing circles one, right? Those tend to be the same. So brought my special math shoes today. These are shoes that I had back in college, and they were these green Converse that I do a bunch of math stuff. And if you're curious about what he's talking about with Euler's formula here, this is that. And it's just it's a reinterpretation of this diagram just in terms of imaginary numbers. So basically Euler's formula says, what if we took this sign leg and we assigned it the imaginary number, right? And boom, basically everything falls out from there. What I it's really interesting, right? Because the first time I learned about a fractal, you know, all of a sudden, when you learn about stuff like fractals for the first time, and fractals are objects that exhibit self-similarity. So a tree is a great example of a fractal, right? Because if you zoom in to a tree, it looks like a tree again, right? And you zoom in on a branch and it looks like a tree again. You zoom in on a leaf and that leaf looks like a tree, doesn't it, right? So that's essentially what a fractal is. Your veins are a fractal as well. Fractals are everywhere in nature, right? And the first time I learned that, it literally changed reality just entirely for me. Like all of a sudden, you know, I was, it had a certain richness that wasn't there before. And every new math concept that I've learned and that I've been able to find like real world or philosophical or sort of social correlates, all of a sudden it sort of almost brightens the world. Like it's difficult to describe unless you've done something like a psychedelic, right? But it ends up being sort of similar to a psychedelic experience where, unlike a psychedelic experience, which is sort of very internal, it's sort of an experience that you can share with other people, and it is wonderful. One of my favorite things about sharing math with people is and maybe I didn't do it so effectively this time, but essentially watching their face light up when they see the universe in a way they had never seen before, right? And that usually sticks with people, and it's kind of fun watching people run around applying this new pattern that they see, because see, patterns exist in your head sort of first, right? And then you see them in nature, right? Sometimes you see the pattern, you know, in nature, and then boom, it pops in your head and you don't know how to label it, and then you see the similarities. But once you actually have a pattern named for surezies, right, then all of a sudden you start running around and seeing it everywhere, right? So that is a magical experience, and it's additionally magical too when you think that literally the difference in many ways. I mean, there's obviously material science and industry and all that stuff, but the difference between people in the Renaissance and us right now is the fact that we use imaginary numbers and they don't, right? Like that's literally a huge part of why people in the age of exploration were able to navigate in the world, is because they had more clear ways of calculating than previously, right? Like it is totally wild that a main difference between us and our ancestors is literally our ability to more precisely calculate stuff in the universe, right? And that involved experimentation for sure, but it in large part involves math to back up that experimentation, right? So a certain sense in which, okay, how about this? Math has helped me, I've been thinking about this, that if you're familiar with the different types of geometry, right? There's like hyperbolic geometry, there's spherical geometry, there's Euclidean geometry, right? Euclidean geometry is the geometry of a plane. So you could put the coordinate system on this floor and it would make a lot of sense. Spherical geometry is the coordinate system applied to a globe, right? So latitude, longitude, think about it like that. Well, it turns out that the difference between Euclidean geometry and spherical geometry is basically one axiom, and that's the parallel line axiom, right? The Euclidean geometry version says that there's one parallel line next to every line, right? There's you know, essentially there's only one line parallel in terms of like there's only one direction to go, right? So if you pick a line, you got a line, you pick a point off that line, there's only one parallel line through that point. That's what that's what Euclid's fifth axiom was. For a long time, people tried to prove this axiom because it felt like it should be something derivable from other axioms, right? But then in the 1800s, Gauss and kind of independently from another guy found that you could consistently create a geometry through rejecting that version of the axiom and say there are no parallel lines, you know, given a given line. And this is true for a globe. There are no lines that would go through the antipodal points of the globe, the opposite points of the globe, right? You know, there's only one line through those points. So all of a sudden you have a totally different contradictory geometry, and somehow our universe contains the geometry for both. You see what I mean? So essentially what ends up happening is we see that there are multiple maths, right? Like, so the British are actually correct when they say maths. There isn't just one math. Our universe is composed of many different maths, right? And different maths are applicable in different scenarios, right? And will illuminate for different scenarios, right? So there's a sense in which there's a lot of true statements in math that are not real. They're not realizable, right? And there's, you know, plenty of real things that are really difficult to model with math. So that was kind of helping me see that there is a difference between truth and reality, like for real though, right? Actually. Let me see, there's another point, which is to say, you know, the kind of math that I think theosophical people would be a little bit more interested in, and that I'd be interested in doing another talk on, and it'd be kind of easier to gear towards, would be essentially permutations. And permutations are how you reorder sets of things, right? And the permutation is a more general form of symmetry. So if you think about the Enneagram has permutations in it in terms of, you know, the ways in which the lines and the numbers are, you know, arranged with each other, right? So let me see, we're getting close. Yeah, we've got some time.
A strange question, but going back to talking about metrics and 12, and I know I was raised on yards and inches and so forth. So, and I know that when metrics was starting to take over, people were saying, "Well, America's really falling behind the rest of the world." But you brought up that 12 was a much more better way to handle things. 16. Comment on that?
Yeah. So oh yes, I'll repeat that. So basically, the question was, you know, it was said back when the rest of the world was adopting the metric system that the U.S. was going to fall behind and you know, be backwards country, right, for having a sort of base 12 measurement system as opposed to, and it would seem that I'm giving a you know, an apology for base 12 based measuring systems versus base 10 measuring system. And the answer is absolutely yes. And you see, in 1066, the world went totally wrong because William the Conqueror fucked up England, right? Essentially, the French, you know, went over through conquering the English and totally messed a lot of stuff up. Well, you'll notice who is really hawking the metric system. It was the French, right? So as usual, everything that ruins the world comes from France. I'm taking a hard anti-France stance here.
Maybe a little far out, but you talk about philosophical and math.
Yeah.
Math systems. I have a brother who's a physicist. I got a solid geometry, and I said, unbelievable. But philosophically and math, you ever look at Johnny von Neumann?
Oh, von Neumann? Is that the mathematician or?
Yes.
Yeah. So actually with von Neumann, it's kind of interesting because he was one of the first computer scientists, right? And he also developed, along with Alfred Whitehead and Russell and some other pretty big high caliber names, set theory, which is the current model that maths uses, right? So for the longest time, math was thought of in terms of geometry, right? And there was a huge shift in the early 1900s where instead of geometry, folks decided to think about it in terms of essentially boxes. And that's what a set is. A set is just sort of a mathematical box. So those folks were thinking real hard about like the limits of logic and the limits of language, right? I mean, there's a lot of that stuff going on with Wittgenstein. Wittgenstein and Russell were close friends and very much talked to each other all the time. And Wittgenstein would have known about Russell's paradox, which is sort of easily encapsulated with a set cannot contain itself, right? So a box can't be an element of itself. And the reason why this is important is because early set theorists were talking about the set of all sets, right? Turns out that's not possible, right? So this has been given the philosophical name of the barber paradox, right? So it's like the barber is the person who shaves everyone who does not shave themselves, right? So the question is, who shaves the barber, right? Because if the barber does not shave himself, right, somebody else shaves him, then he has to shave himself, because by definition, he's the person who shaves everybody who doesn't shave themselves, right? Well, and then the issue is, if he shaves himself, right, well, then he can't be the barber, right? Because he's only the person who shaves everybody who shaves themselves, right? And he shaved himself, doesn't shave themselves, right? So we've landed at an issue, right? So you have to, the point of that isn't to say barbers are impossible. The point is you have to be a little bit more careful than saying, you know, the barber is the person who shaves everybody who doesn't shave themselves. It seems like an easy way to put what a barber is, but it turns out it's not accurate. It's not a good way to put it. You just say a barber is a person who shaves some people, right? And that takes care of it. Von Neumann did a lot of thought around computer science too, right? And there was another really famous mathematician who literally helped win World War II for the Allies. God, I'm blanking on his name all of a sudden. Goodness, he's a really interesting. That guy has got a, God, what is his name? Turing, Alan Turing for Turing machines, right? So he's one who literally invented computer science as, thank you, who is Noel to everybody. Nice, Noel's got it. So he's the guy who invented Turing machines, which is the start of computer science, right? And he's a really interesting fellow to look at, though, because, you know, again, he kind of gives us a window into what that society at that time, how they dealt with somebody who is undeniably a hero, but also not really fitting into the overall like social structure of the time, because he was famously gay, right? And so then they were like, well, what do I do with this guy? This guy's a hero and gay. Like that's an issue. Like so it's really interesting seeing the establishment try to figure out what to do with him. And he had a little bit of he had an unfortunate end as well, but at any rate, so Turing was a really important philosopher around, you know, AI as well, because he came up with the Turing test, which was a thought experiment, one of the earliest thought experiments to be like, well, what would artificial intelligence look like? And essentially what he said is like, well, artificial intelligence is fooling a human into thinking it's human. That's a decent measuring stick, right? So I won't go off on that rant, but I don't know that this particular talk has specific like philosophical touch points, right? Like it's not like this explains you know, the three principles, right? The three theosophical principles or anything like that, right? But I think what it's kind of like, is incense sacred? You know, what is sacred about holy water? Right? What's sacred about meditation? You see what I mean? Like I think the Zen people kind of get it right, where they say like everything is sacred and nothing is sacred, right? Like, but sacredness is sort of what we define it, what we just choose it to be, right? One of the reasons why, you know, the loss of the temple was such a big deal to the ancient Hebrews, the ancient Israelites, was because it was like, oh my God, God is allowing his sacred space, the thing that he decided was set apart from the universe, literally a tiny slice on heaven on earth, to be desecrated by foreigners who are ruining everything, right? So you know, sacredness is in some ways maintained by us. Like we're the ones who identify what is and is not sacred. Like if, you know, if I walk into a Buddhist temple, I actually don't know what's sacred or what's not sacred, right? If you walk into a church, you've never been to a church before, there's this pool of water, it doesn't mean anything to you, right? Like there's a certain sense in which sacredness, there are some places that people walk into, and they're usually like natural places or closer to nature, that everybody kind of just agrees is sacred, right? You walk into a forest or bits of Mount Sinai, and you're like, holy shit, this there's something here. This is set apart. Well, why is it set apart? Well, it's because it's totally different than your everyday, your everyday city life or even like country life. It's outside of your normal existence, right? And I think that's what sacredness tends to be, is it's outside of your normal existence. And so sacred geometry is geometry that's outside of normal geometry, right? So it's not, and that's why I started with at the beginning with the notion that it's either the geometry of sacred land, of sacred sphere or the sacred place, or it's geometry, the set of geometric methods that we set apart as different and sacred from other measurement tools, right? So we're kind of the ones that are noticing that set apartness, whether it be the specific geometries that it comes up with, or whether it's mapping out the spiritual space, like everybody gets very excited about the golden ratio, right? And that's a key component of sacred geometry for a lot of folks, right? And there was much made by the Greeks about the golden ratio and whatnot, so that was seen as a sacred ratio, a ratio among ratios, is so to speak, right? Yeah, people are getting really excited over here. Yeah.
I was just going to add on to that. It's what you're describing is a language to describe the relationships that show up in nature that
Yes.
are predictable. They replicate, and it was noticed and discovered, and a way to describe and discuss this language was developed in order to describe and be able to discuss this wonder of pattern that admittedly said, you don't have the time today to take us deep into that, but the abstract, the formulas that you showed us is the language to describe those magical relationships that are predictable and show up in nature.
Right. And all I'm trying to do here is to just kind of demonstrate that hopefully those formulas are a little bit less scary than you might otherwise think, because they can be scary for folks, right? And that, like, we can actually get pretty technical while hopefully still keeping the thread, so to speak, right? So somebody is trolling me, asking if math is discovered or invented. No, I think that math is so since math is a pattern, right? It's both discovered and invented, which is a total cop-out, but it's true. Because as we refine our language, we discover more nuances within the patterns that we already had. So as we get increasingly sophisticated patterns, we find new patterns amongst those patterns, right? So essentially we we invent the axioms, right? The axioms are the mathematical sort of statements that we just take on faith and say, we could reject those anyway. So we'll just accept them for the sake of argument. And then we argue for a whole bunch, and then we discover a whole bunch through that argument, given that system, right? So we kind of, we invent the axioms and discover their results, is what I would say. And I think that's actually a reasonable way of putting that I'm sure neither side is happy with, but it's better, all the better. Go ahead.
So the natural, we're addressing this natural versus whatever, that's
Supernatural.
For example, you're talking about the golden mean and all these things. What about modern things like understanding curved space-time, being responsible for gravity, for example, which is all discovered by mathematics, right? It's not discovered by any other means other than by mathematics, and yet there's no more fundamental principle of nature than gravity. So very powerful in that way.
No, it is very powerful. Well, it is sort of like showing us stuff that was sometimes there in plain sight and sometimes not there in plain sight. So what I mean by that is that anybody could have looked up in the sky probably by the time of Galileo, certainly before Einstein, right before Einstein, and be able to see some of the events that Einstein was seeing, right, predicting, in particular gravitational lensing, which is where light bends around highly dense objects, and you could see, like, say, a galaxy that's smeared out into a circular pattern that just doesn't make sense otherwise. Well, nobody really knew to look for this up until Einstein, right? And it turns out finding these examples was pretty difficult given those times. Like people literally had to go to the South Pole, right? And during a particular version of an eclipse and be able to look right here at the sky and all of these things, right? Like there was a lot of mysteries that people knew about, like why does Mercury go retrograde, right? And what's the pattern of Mercury going retrograde anyway, right? And all of these things, so there were some mysteries that are described by math, right? Better once we have a better understanding of it. But there's a lot of stuff that we didn't even know was there until the math predicted it. And this is something that you see physicists or natural philosophers and mathematicians kind of playing this game with each other back and forth, where the physicist will see something and then a mathematician will be like, oh, you know what? That's a really cool pattern. I'm going to steal that, abstract it, and then come up with this totally crazy stuff that has nothing to do with reality. And then all of a sudden, a physicist is talking to a mathematician and the mathematician's talking about their really exciting discovery. And the physicist is like, oh, snap, that actually sounds exactly like this gravitational situation I'm talking about, right? So Einstein was using cutting edge, what at the time was called tensor calculus. I mean, still is today, but this was discovered but like literally 10 years before by Riemann, right? Well, Riemann was one of the top students of Carl Friedrich Gauss, right? And so Riemann came up with basically the way of describing any geometrical curved space, right? And then Einstein used that to describe gravity as we understand it today, right? So there is a really fundamental, like I said, sometimes you see the pattern, it goes in your mind, and then you see it everywhere, or you already have the pattern in your mind, and then all of a sudden, the pattern is transmitted from like me to you, and then all of a sudden you see the pattern everywhere, right? Like it's sort of this one leads to the other a lot of the ways, right? And this is why math feels discovered and invented, right? Because you see patterns all the time, but sometimes you invent patterns and then you see them, right? It just depends whether it's discovered or invented. Really just depends on your position in this discovery process. So I think we'll leave it there. And everybody already knows me, so you can ask me questions through the various channels, so that's good. You're welcome. Oh yeah, hey, and before you go, if you're especially in cyberspace, personal friend of mine, go to the Theosophy Society and donate $5 to $10 if you would. Thank you. And thanks everybody for coming. I appreciate it. I hope to do a talk that's actually a little bit more sacred geometry based, but hopefully this kind of spurs people's curiosity. If there's something that I talked about or some math thing that you're excited to learn about, maybe ping me and we'll put another sort of explaining the mysteries of stuff that you otherwise wouldn't know. So thank you everybody.